So, hi, I'm Philipp. I wanted to talk a bit about semantic search, new solutions to old problems. We'll see where this goes. So, I wanted to talk a bit about like classic search, what you have probably already used, or who has already used search in their past developer life so far. Probably you have done classic search, and I'll try to show you what is classic search, what is semantic search, or the new hotness around vector search and hybrid search, and how all of these can be combined. We'll quickly take a look into what is a model. Who was in the previous talk in this room about large language models? A couple, okay. We'll briefly touch on those. I'll also try to go a bit beyond where I think search and large language models can cooperate rather than compete. And we'll dive into all of those and see how that goes. So, I work for Elastic, the company behind Elasticsearch. You might have used Elasticsearch. I think it's by far the most widely used search engine at this point still. Hopefully we can keep it that way. And I'll show you my examples based on Elasticsearch, which might relate to what you have been using, but it will translate to pretty much any other semantic search solution one way or another, or also a classic search engine. So Elasticsearch has a REST API that you can interact with, but Apache Lucene is the library doing the search under the hood for that. And that's true both for the classic search as well as the vector search that we'll be touching on. So everything I'm showing you here is to some degree more or less part of Lucene as well, though we have a lot of things built around that and in the ecosystem. So when you do, come on slides, no? No, that was too much. Back. Yes, here. Let's look at a simple example of like how search works. Who remembers in Star Wars when he was doing that hand gesture, what was the quote in Star Wars? Yes, exactly. These are not the droids you're looking for. And we'll take a look at that to see what search does with that. And for some reason, this is super slow to change the slides. Because you can already see them. So what you generally do is, you have a sentence like, these are not the droids you're looking for, and you have your text that you want to search. And what you normally do is, you run through a so-called analysis that you filter out some pieces that you need or don't need. So for example, here, the first thing I do is I remove the HTML, because nobody's going to search for these emphasis tags here. And then I tokenize. Tokenizing is basically breaking up the individual words. So these are not the, each of one of those is a token. In a Western language, tokens are very straightforward and simple. It's pretty much punctuation marks and spaces that break up words, and each one of those gives you a token. Asian languages can be much more complicated, but we'll skip over those for today. Then we lowercase everything, because most of the time when you search, you don't care about if this is uppercase or lowercase. You remove the so-called stop words, which are very common and just appear everywhere and don't find something very specific. And then you can do stemming to basically remove or reduce the word to a stem. Because you don't care if something is an adjective or an adverb, if something is singular or plural. You more or less care about the concept that you want to have. So it is language specific, where you try to figure out what is the actual word that we're talking about here. Anybody wants to guess what would be the output of, like, if I run this through this analysis pipeline, and then we're ending up with these are not the droids you're looking for, what will be the end result that you get out of this? Anybody wants to guess? What are the tokens that we're extracting and how will they look like? Yeah, so you don't have to take my word for it. We can actually just try that out. And my internet connection, no, is kind of maybe half dead. We'll see if I still get that. So if you run this, so this is a standard request, and for some reason, well, let's see if that request goes through. So what you get out of this is droid you look. This is what the search engine basically extracts for you and would store. So you can see the looking gets cut down to look, so that is the stemming, because we don't care about if it looks, looking, whatever, we care about the concept of look. And all the other tokens here were stop words that we have just thrown out. And you can see we have a couple of extra things here. We can see start and end offset. Any guesses why these might be relevant, why you want to keep them? If you do something like highlighting, that's so you wouldn't need to analyze the text again, but you could just say like, you searched for look, and the thing that contains look here starts here and ends here, and you could just have that highlighting or marker there. We also have a position. Anybody wants to guess why we have a position? Yeah, proximity, or just a simple phrase search where it's a very weird phrase, but you could just say like droid U, which is not a very common phrase, but you could see one has basically position n and the other one n+1, and this is how you could, without really looking at the underlying source again, you could figure out what was a phrase or what was right next to each other. So this is how what you would extract. What is the obvious downside of all of this? It's very much like based on these tokens that we have extracted. And this is kind of like the difference to the semantic search, where with semantic search, what you're mostly interested in, you want to capture the meaning of something or the context. Whereas this one is very simplistic because it looks at, okay, we have droid, and if you search for droid, it will find that. But if somebody looks for robot or machine, they will not be able to find this because it doesn't match. And yes, you could define synonyms. For example, you could, one of the other examples I always do is, let's look at that quickly. No, I am your father from Star Wars. Anybody wants to guess what remains if I run this through the analysis? You end up with, I am your father. This, by chance, doesn't have that many stop words. Actually, the English stop words are very few by default. So you get these, I am your father. And now you could say, okay, I define a synonym that says dad is the same thing as father. So if somebody searches for dad, they also find father. But this is a very tedious and manual process, and there's not much meaning behind this. The advantage of this is it's very easy to understand, it's very fast, and it scales very well. And in IT, oftentimes, dumb but fast is good enough, or it was good enough for a long time. But this is then where semantic search is coming in, where we say, we don't just want to have dumb, we want to have something that is a bit smarter. So let's get back to my slides, and I have lost my internet connection and the slides. Well, I'll just show you the slides like this. Let's make this full screen. I hope this will be good enough. So the idea of semantic search is that you have the meaning and not just the literal matches that you have. So if somebody provides the right tokens, you can easily find that, but you really want to go beyond that literal matching, and you want to get that meaning. So one common thing there is that vectors are kind of extracted by the machine learning model, and you can store those vectors to find something similar, which is not just based on these tokens, but on a similar vector model. And what the idea behind all of this is, you have some input, and the input could be a text document, but it could also be an image or an audio file. You have a machine learning model that can transform them into a vector representation, so a vector like back in school when we had 2 or 3 dimensional vectors. These normally have way more dimensions, and what you want to express with a vector is that something is similar to something else. And you would store these dense vectors, which is basically an array of floating numbers. You store that, and when somebody searches, you have the search query coming in, you make the vector representation of the search query, and then you just try to find something that is close in kind of like the vector representation to what you had before, and that is the search result that comes out. So it doesn't rely on having the same characters, but it's really if you have the right model that can transform your input into some representation of a vector, you can find something that is similar in meaning and not just in characters. And the nice thing is that this also then works for not just texts, but also images and audio files. So you could have a vector representation for an audio file, and then you could look for something that sounds similar. Even if the lyrics don't matter, you just want to have the sound. And you need to have a transformer or the machine learning model to extract like how something sounds. We'll get into a bit more the models in a moment. So what is this vector that we're talking about? My very simple example, to stick to the examples that we had before, let's say we had, these are not the droids you're looking for, and no, I am your father. And I basically just count, or I extract the tokens as they first appear. I count how many times are they appearing. For example, R we have twice here, and these are not the droids you are looking for. And then I try to give those a vector representation. So these are basically the dimensions, and then I just count like these appears in the first document once and 0 times in the second document, twice in the first document and 0 times in the second one, etc. So you get a very sparse vector, but this is the vector representation that you could build out of this. This is not what modern machine learning models are doing. This is just to give you an idea of how a very simplistic way of how to extract vectors from a text could work in theory. And it's called bag of words, so you basically just put these words together. It's mostly zeros if a term doesn't appear in one specific text, but let's say this is good enough for this example here. I'll move my notes down here. But it's closer to a cartoon. And then you might find this elk here. Or if you, for example, say, I want a bird, but one that is more realistic, then you would end up here on the vector. And of course, the vectors are not just two-dimensional, because two-dimensional is very nice to draw out and easy to understand, but the real vectors where you transform your data would be n-dimensional, and the n would be something like 90, 300, 1500, or something like that. So you have way more dimensions, which I couldn't easily draw out, but the idea here is really to have in that vector space in all the dimensions, you have a representation of what something is or means, rather than just having an exact match. Because otherwise it would be very hard to say like, how close is this to a bird, and how realistic or cartoonish is this? And this is what you get. You just need the right model to give you that representation out of an image or a text. So all of this works very well if the model works well for the data that you have. If you have a model that doesn't work so well for your data, you will also get much worse results. But this is kind of like the precondition of what you're trying to do. But you get these vector representations of your data in whatever form and shape you have them. So what is this model? The main thing where these are living is Hugging Face, which has a ton of either proprietary but also open source models that you can use to transform your data. And it's kind of like the source to get models from, to extract meaning from images, text, videos, whatever you have. In the case of Elasticsearch, for example, we have a library that could load one of these models into Elasticsearch and then run them in Elasticsearch itself. So you don't have to, because you could run this standalone, so you could take your input, throw it against that model, get the vectors out of that, and then store the document with the vectors in a document store. Or you could just do that in one step, where you do that inference or creating the vectors in one single step when storing the document. And you basically, this would be a concrete example where we take the BERT Mini-LM L6 model that might work well for many text cases, how to import that, and then you have that available and can use that. But these models can do more than just trying to extract meaning. They can also do, for example, named entity recognition. So for example, named entity recognition would, in a text, figure out this is potentially a person, this is a place, a country, a city, whatever, and it could then annotate the text. And then you could do in further steps, you could say like, what are the relevant entities that were part of a text? Or you could also, for example, if you store logs, you could redact personal information by saying like anything that seems to be like a person, I want to redact out from my logs. So those models can come in handy in many places, either to find something that is similar, or to find, for example, a named entity, or to get that text embedding out, what I've shown you, the vector representation of a text. Or you could classify a text, what type of text is this? You could also do something like sentiment analysis, like is some text, is somebody happy or unhappy? And then you could, for example, search over all your user interactions and search for the comments where somebody was the most happy or potentially unhappy, if you want that. You also can do things like question answering. So for example, you have an input, and rather than just giving them the source document that you have, you could use the source document to actually answer a question. This is a bit what ChatGPT is doing, and I'll show you an example later on. So there are many shapes that models can take and different tasks they can do, and all of those the models are always built for a specific task or thing to do. But they have been trained to do that, and then you can run this inference in whatever system you're running here. And to start off, Hugging Face has a great collection for text data. For images, OpenAI has something called Clip that can do image recognition very well. We'll get to hybrid scoring a bit later, but you could, of course, build your own models as well. So if you have a data science team and you have a very specific data set that is different than everything that is out there, or you think you can do a better job than the models that are provided for you, you could totally build your own models and do that vector representation of the data that you have as well. So how do you search it then? So what you do is you have data that is coming in, and you can either store the data directly without vectors, or you could throw your data against the inference API, and then it stores it with the vectors, stores your data. And the inference can happen with the PyTorch model, which is probably the standard almost in how to generate models or manage models. And it can then generate the vectors for you, and you store both the source data and the vector together. And then when the query comes in, it also gets this inference, so it also gets the vector representation. You search for similar vectors in k nearest neighbors. So this can be a search that can find in this n-dimensional vector space, can find the things that are the closest to what you have stored. And then you get those documents back. So that is really the idea here, that you store these documents with the vector representation, you find everything that is close by, and then you return those documents. And that is really the main difference here. It is a bit more complex and has more parts than classic search. It's also slower and takes more resources because it's much smarter, but that's the trade-off of what you're doing here with the vector search. So to give you an example here, we have some source document, and then either we store it directly, and if I could play this if I had internet, then this line would not be visible at first. This would be the standalone document that you have that you're storing. But you can then do this inference where you, for example, use whatever PyTorch model you want to run here, that you then store this vector representation. So this is on the field description. So here you have description, our best-selling, whatever long description here. And this is then the vector representation, an array of floats that describes this description not just on tokens, but in terms of meaning. And then when you search, you can say, I want to use whatever model I have here, and I want to find summer clothes on that description. And what is nice that you can, on top of the vector search, where you say, give me all the summer clothes, and then it will hopefully understand what is summer and what is clothes and give you something that is close in the vector model. You can also filter that on top. So you could just say, like, only the subsection of the women's department is interesting in this specific search. So it's vector search plus classic filtering to avoid any false positives or to reduce down the set of data that you want to have. So how does all of that really work in terms of vector search? There are multiple possible implementations. One of the most widely used ones, and the one in Lucene, is called Hierarchical Navigable Small Worlds. And it looks something like this. You have multiple layers. So the dots are basically your documents. They're kind of like in your vector space. And then you have different layers, and you start on a layer that has fewer of the dots, so you can basically navigate more easily to the area of where your search hits are. So basically we start here in this red dot, and we say, and we know for the thing that we're searching for, this other dot is closer. So we're moving over here, then we're going a layer down, then we have a few more nodes, and a few more vectors between them, and then we know out of those 4 nodes here this one is the closest one to the search result that I want to have. So we move over to this one, we go a layer down, and then we say, this is actually the area that we are searching. So you're moving to that one. So it's basically in a multi-step approach to approximate how to get closer to the area that you want to retrieve. And this is one of the two approaches that are built in and you can use. So you can either brute force this. You just, if you have very few documents, you could just calculate the distance between all the vectors, or like you search for something and then you calculate the distance to all the vectors that you have stored. And if you have very few, that will kind of work. But if you have, let's say, 1 million documents, like calculating 1 million distances is a very expensive operation. And that is when you want to use this, this hierarchical navigable small worlds, that you kind of like iteratively get closer to the problem and then just work on that subset of the data. And that will make your search very fast. It's extra work when storing the data to build that HNSW structure, but it will make your search a lot faster as you go on. And this is just a representation of where is the cutoff point between how selective is a filter, and like if you have a filter that only finds very few documents and you have a very small set of documents that you want to retrieve, you can brute force that. But if you have a very large number of documents that you need to search, you want to use this dedicated data structure to actually make that approximation much faster to get to your search results. I think we can skip this one. This is more an implementation detail, how that skipping and finding the right subsets works, but that might go a bit too far. The general discussion here, and that is also one of the bigger performance impacts, is how many dimensions do you want to have? And the naive assumption would be the more dimensions, the better, which is also not wrong. The more dimensions you have, the more things you can express, but also the more expensive, because you need to calculate the dimensions, you need to store them, so it will take a lot of space, and also finding something that is similar will be more expensive the more dimensions you have. So that is a trade-off between what you want to achieve and how many dimensions you can actually afford for the amount of data that you have. And how many dimensions you have really depends on the model. So the model will then tell you, for it to work, it will need n dimensions, or maybe it has multiple implementations with different sets of dimensions, and the more dimensions it has, the more fine-grained the results can be, but also the more the more expensive and potentially slow the calculations will be to find those. The current limit in Lucene and Elasticsearch is 2048 dimensions. We've mostly changed that because OpenAI has right now 1500 dimensions, and people wanted to use models like that. If we want to do more in the future, we are not really sure yet, because like I said, there is quite a performance overhead to that. So just to reiterate that, lots of dimensions need lots of memory to store them. They're slower to index, and they're also slower to combine as you get more data together. You can do a couple of tricks of how to do that. Either using fewer dimensions, or the other thing would be, for example, to change the precision of your data. So rather than having a float, how many bytes do I need in a float? 4, exactly. Rather than having the precision of a float, I could just use a byte. So I use only 1 byte. So you only need 1/4 of the amount of A disk and B memory to store or keep those vectors in memory. But you of course have much less precision. Though it sounds like your results will be 4 times worse, but in our in our tests, like for many scenarios, like having the precision of byte is good enough. And other implementations I've seen, some are using a data structure that uses 2 bytes rather than 1 byte, but most of the solutions have multiple precisions that you can use based on the dimensions that your vectors have. The other thing that you could do is you could reduce the number of dimensions that you have. And there is something called the principal component analysis, which either I have never learned that at university or I have totally forgotten it. And I don't know if anybody still remembers that from university. Okay, then at least I'm not alone. Because I have absolutely no idea that we did that, or maybe we just didn't. But there's a way basically that, again, you're giving up some precision, but you can reduce the number of dimensions to then reduce the amount of memory that you need to have. But again, you need to have some pre-existing data, I think, to do that calculation and to do the transformation. So you need to have a more or less stable set of data. Let's say if all your documents are kind of the same, after 10,000 documents, you could do the calculation to reduce the dimensions. Or you do it at the very end, but then you need to do all of those calculations again. But there are ways to reduce the dimensionality. One word about benchmarks, because that comes up again and again. There are a lot of very bad benchmarks out there, which is often more like benchmarking. And it normally looks like this, that somebody benchmarks some system against some other systems, and then you say, under similar conditions, this system was much better than the other. Like here, we're saying that under similar conditions, the squid is much smarter than the house cat, because the house cat has been drowned and the squid is still solving its puzzle. And this is what you get in a lot of benchmarks out there. This is my favorite benchmarking comic. What is quite nice, there is one independent repository, ANN benchmarks, that actually benchmarked a lot of different systems and their implementations, and there you can actually look up how fast different implementations are. Lucene right now and Elasticsearch are kind of in the middle of everything. We have a couple of optimizations coming that will hopefully move us further ahead. Right now, like native implementations that are not based on Java, for example, have a bit of an advantage, but also with some of the features, I think around the vector APIs that Java 21 will bring, we will also have some hopefully good performance improvements there again. So one of the things that is kind of holding us back, but will also move us forward soon, hopefully, is what Java has to offer around some data structures to make vector search and comparison faster. I skipped that slide, that's not so relevant. What is hybrid search now? We've talked a lot about like vector search and how those are combined. Hybrid search is kind of like maybe less or not so surprising that you combine the term-based approach with the vector-based approach. And why would you want to do that? The thing is, vector search is very good about extracting meaning. But if your search query is only like 1 or 2 words, it will probably have a very hard time extracting a lot of meaning from that, because it just doesn't have a lot of context. There, term-based approaches are still very good, because you can just look for all the direct matches of that term. You don't need that complicated vector search because you're just looking for the terms that match. And you probably want to combine the two, because people often expect both the term that they entered to be retrieved, but they also hope that you can get some more meaning around your terms and find meaningful documents. And then you can combine those. And this looks like here that I'm searching for summer clothes, and then I also try to search for the same vector representation, so I both hit the tokens summer clothes and whatever meaning I can extract from that in my search. The one small downside for this is that these two have very different scores, and scores is like the relevancy of how relevant something is. Because this one here has a positive number, but it doesn't have to be 1, it could be 5 or 10 or something like that as well. And this one here, depending on the similarity that you're calculating, can also have a different range. And then you need to manually kind of like adjust those two ranges. And that's what we're doing here with this boost. So this one, the relevancy here, we're basically multiplying by 0.9, and this one with 0.1 to adjust the scores and make them kind of even and relevant. We have just added as a first implementation something called reciprocal rank fusion, which basically is an algorithm that adjusts or normalizes the scores against each other. So you can throw different calculations of scores together and combine them, and you don't need to care about this manual boosting anymore. It will basically normalize different calculations and scores against each other to find the most relevant things. And then it can retrieve those. Just to give one more example, because you can also retrieve multiple vectors. So here we are combining the token-based matching of summer clothes. Then we're searching on an image. Obviously, the person uploaded an image and said, like, I want to find a summer cloth that looks something like this. And then we're also searching the title field with this vector. So we have two different vectors calculated by two different models to find something that is similar. And you can combine all of these. And as you can see again, here we're just using manual boosting to try to adjust the scores of all three. But with reciprocal rank fusion, you can automatically adjust those and just combine vector search and token-based search on various fields together to find the most relevant things. The downside here is, of course, that this is getting more and more expensive the more vectors you calculate and then need to search. And then we have also added something else, which is not vector-based, but it's a domain-independent model that basically tries to extract the most meaningful context here. So I'll just show you because it's probably easier to show than tell. If my internet connection is down, then I cannot show you, then I'll just show you on a slide. So what this does is we're running our text. These are not the droids you're looking for here against this machine learning model. And it basically looks at all the terms and says, like, in terms of context, these are the things that I think are similar. But rather than calculating a vector and having then to do an expensive vector search, it's just adding with a specific weight various terms that are most similar. So for example, it knows that ship is kind of similar. I don't know why dragon is similar, but maybe the text has some meanings of dragon. So it really tries not to just go for the terms, but it really tries to extract some meaning and find something meaningful in another text. So for example, if we are looking for, I don't know, robots now, it would potentially find this. Also, if you look for Lucas, and I'm not sure if this is George Lucas or another one, but it automatically attached Lucas to this text and says, like, if some text has something that matches to Lucas, it would find this. So you can find similar texts without going to the vector search, but just by having weighted tokens basically attached to this to find similar texts, which is another machine learning model to extend your texts and extract the meaning, but without vector search. So there are in the hybrid search space, there are multiple ways to calculate and find similar things nowadays. Then there's the question of ChatGPT or large language models in general. What are some of the downsides of using large language models? They're potentially expensive, yes, that is correct. Anything else? Delay? You mean that, what was the cutoff point for ChatGPT, for example? You mean the response times? Yes, that is also true. Response times are a thing. What I'm more going for is that the cutoff point for ChatGPT was September 21. So it only learned things until September 21. So for example, if I had internet connection, but I don't think that will work right now. If my network is completely down, let's see if I can connect to my phone. But you probably have used ChatGPT yourself. For example, when I would ask it, let's see if we get more network here or not, okay. If you ask it what is the current version of Elasticsearch, it I think tells you 7.14, because that was the current version in September 21. But that is, of course, way outdated by now. And all of the vector APIs that we have added since then will not be searchable. So that is one of the big downsides of this model. So what you can then do is, and I tried this once to ask ChatGPT what is not great about ChatGPT, but then it errored out, but it can answer that. Like sometimes it's just overcapacity, and that I think was more of an artifact. So one thing that you can do with large language models is you can use them to extract meaning, but then you prompt them to answer things with a specific question. So what we have done here is we have taken our documentation, because we have added a lot of features since September 21, so we want to have that searchable. We have indexed that information, and then we have built some application that we call Elastic Docs. And what Elastic Docs is basically doing is it has a small Python application. That Python application takes the search query that you have entered here, forwards it to Elasticsearch and retrieves the top 5 documents that are relevant for your search query. And then it takes those documents, hands them over to OpenAI and prompts them and says like, answer the question that has been asked here, but only answer it with the 5 documents that we provide from here. So you basically provide your own information base and prompt ChatGPT to answer just with that, which is great because A, you can insert more up-to-date information, but also if it's company-specific information that you rely on, you could also prompt it. So for example, if somebody searches like, what is the life insurance of our company? ChatGPT won't know in general what the life insurance of your company is. But you could retrieve the relevant policy, give it to OpenAI, and then OpenAI or ChatGPT would summarize your life insurance, for example, and give you the right answer. And it can have this conversational interaction with ChatGPT while still just using the information that you give it that is both current and potentially private to you. What is the downside of that? You still need to give your private, at least the top 5 documents or whatever, to somebody external, which you might not want. But for that, there is this full tree of large language models. The one that are kind of like filled out are open source. And here you can see there are a ton of open source models that you could run yourself. So you could store your own private information in whatever data store you have your own large language model run yourself, so not by somebody else, and then basically you feed that language model with your own private information or within your own network or under your own control without giving it out to anybody else. So you still get the advantage of having that question answer style or summarizing feature of a large language model, while still having current information and custom information without doing any custom training or adjustments otherwise. And that is kind of like where we see that large language models have totally their place, but they're probably not where you want to store all of your current information, or you don't want to retrain the language model all the time with new information coming in, but you more or less want to prompt it to build on top of the information that you provide to it. And then you can kind of like marry search in a traditional sense, and for the search, in this example, you could use token-based search, vector search, or hybrid search, whatever you want. You can extract any type of information you want and hand it over. So you can marry that search aspect with your information with a language model to extract that. So to wrap up, search or semantic search nowadays is often made up of language models, often third parties or your own, and then you can have a vector representation of text, images, videos, music, whatever else you want to have. You can have still token-based search, and you probably want to have that because people expect like the specific token that you have searched for to come back. And then there are other language models that are not vector-based, like ELSER, which enriches text as well. You can combine all of those, and that is then what search in the semantic search context can give you. So it's kind of like a much smarter combination of these things. Yeah. So in the end, it's still all search, and you can call it vector search, hybrid search, semantic search, AI search, ML search. There are various terms being put on top of that, but we're still going just for the term search as its core itself. I think we are pretty much exactly at 10 minutes. Any questions? Also, if you want to have stickers, I have a lot of stickers up here, so don't be shy and take the stickers at the end. Any other questions in the meantime? Has anybody used vector search with any product already? No? Okay. So if you have a search problem and somebody says your search is bad, maybe vector search is not the first step, but the 5th step or so, because there's a lot of tuning that you can do in search in general, but vector search definitely gives you a lot of new tooling around that meaning around search and not just matching tokens, which, like I said, it's dumb, but it's fast, and it was good enough for a long time. But search has become kind of like a hot topic as well. So there are a lot of new tools that you can use to make the most out of your search queries by now. Any final questions? Yes? So the question was, can you only use vector search with Elasticsearch, or can you use vector search as your own implementation? So there are a lot of vector search products out there. So vector search is like a group. It's almost like relational databases. So it's not just one implementation, but there are many implementations. I don't think that you want to implement this yourself. I mean, you can. And a library like Apache Lucene would give you the tooling, but it's still a very low-level API that you probably don't want to use. Then there are basically two groups of tools. There are dedicated vector search engines that can only do vector search, though many are trying to do or add token-based search as well right now. And then there are the almost larger group, I want to say, or the traditional engines that always had token-based search and have added vector search. So that is kind of like the choice. But there are a couple of, like, both open source, cloud only. There are various vector search engines out there. You'll just need to look at what is the feature set that makes the most sense for you. And also, like, do you need hybrid search? How do you combine multiple search signals? What language models are supported, etc. Obviously, but I'm biased, I think that we have a very complete package for that. That is pretty appealing. But you will obviously need to make your own decision of what makes most sense for you. But yeah, vector search is like it doesn't have as many players, and it hasn't been around for 40 years like relational databases, but it is its own category. Though my take is that vector search is only part of a bigger problem. So I think in a couple of years we will probably move beyond vector search engines as a dedicated thing and just talk about search engines, and then search in the various shapes is kind of like the given that anybody expects from any search engine to support token-based and vector and hybrid search in a combination together, and running the machine learning models for transformation as well. So I think there's a bit of a shift between like some of the newcomers that are very much only vector search, and then like tools that have a broader set. And I think midterm we will move more to that broader set. To me, it reminds me a bit like 15 or almost 20 years ago when NoSQL came up, and then you suddenly had 10 or 20 different data stores that you wanted to use. And at some point, you probably figured out that you don't want to actually maintain 10 different data stores in your product. And you probably want to have like maybe 2 or 3 that are specialized on various areas. And I think with search, it will be a bit of a similar story, that there will be a consolidation. And while you can have a lot of very specialized tools today, you probably in the long run don't want to run a lot of data stores with your data, because it's a pain to run that and keep that up. I hope that made sense. Yeah?
A comment that I would like. Hey, I have a comment that I would like perhaps to have some of your feedback on it. But I was looking at the semantic search, and that for someone like me that uses Elastic mostly for log information, I was wondering if semantic search is more suitable for search in dialogue. What do you think about it?
Yeah, so I think there are multiple, or I think I have 2 points for that. One is, with the very large log volumes that you often have, vector search will be incredibly expensive. I do still think that vectors have their own space for both observability and security data, because if you have the right model, you could figure out, for example, maybe security is an easier example, but observability will be similar, that what is kind of like the shape of a security incident. And then rather than just searching for exactly the same words or so in the security events, you could kind of like look in the vector space what was a similar event. And an event could be this type of user had this type of access and did these 5 actions or so, and that could be one vector representation. And then you look for similar things, and after a time you figure out that somebody broke in, and then you search for similar things. Where it's not just an exact match, but for something that is kind of like in the same area. And if you have a good model that can extract that, it might give you very good hints of like similar incidents in the past, even though some parameters are slightly different, because they're not just token-based. And I think for For observability data, maybe you can figure out like what is the shape basically, or the vector structure of a performance degradation or an outage, and then you can already get alerted either on that early on, or you can find similar ones in the past and try to learn from them. So I think there is the vector representation, if you have the model to kind of like represent it in an interesting way, you will be able to find interesting data that is going beyond like just this very token-based approach. Because right now what we're mostly doing, I guess, is when we're looking for logs, we say like, give me all the logs in the last 24 hours, all the errors in the last 24 hours, and then somebody reads through all the errors. What might be interesting is, for example, that you try to group them together. Maybe you can find a vector representation that groups similar errors together, and then you only have like 3 shapes basically that are standing out from all the data. If vectors are the right representation, or if machine learning can do that in a different representation, is another discussion. But I think there is also this thing where a good machine learning model can extract a lot of helpful meaning from the data, so you don't have to manually read through 1,000 log lines every day. But you can automatically group them together and find the 5 signals that are relevant or standing out, rather than scrolling through all the errors that have happened in the last whatever time. And maybe at some point your machine learning model is even smart enough to figure out what is actually impacting the user and what is relevant, and what is just an error message, but that's an operational thing that is covered by a retry or whatever anyway. So the search itself might have different shapes, but I think the machine learning or the component of an autopilot or copilot is a very helpful thing. And I think at some point people were talking a lot about like AI ops, which was a weird term. And nowadays we're trying to talk more about copilot, where you have some support from a machine learning algorithm that can kind of like group the data for you and prepare that to find similar things. And say like, these are potentially the relevant correlations in your data, or these are this is a shape of log that I've seen before, or something that I've never seen before. So it can give you better search powers with these machine learning models that have extracted some more meaning from something, rather than just a token-based approach, because right now it's often very token-based. And there's a lot of stuff going on around that. It's like, I think for Kubernetes there's one integration into ChatGPT that automatically takes the Kubernetes error message, sends it to ChatGPT, and gives you back the reason why you broke something, for example. So I think there are various things where this copilot system can try to assist you as well with machine learning models. So it's not just search, but it's also security and observability where this comes in. Cool. Any final questions? Otherwise, thanks a lot for joining. Take some stickers, and if you have any other questions, find me afterwards. Thank you.